Welcome to this explainer. I am absolutely thrilled to have you here today. Listen, if you've ever tried building a massive Java project, you've probably run headfirst into a very specific, incredibly frustrating wall. You start writing classes, you create interfaces, you add more and more files, and before you know it, all your code is just dumped into one giant, completely unorganized pile. It becomes literally impossible to find what you need, and worse, you start running into these nasty naming conflicts. Well, today, we are going to solve that problem entirely by mastering Java packages and access protection.
We've got a fantastic roadmap for you today. We'll be looking at 1. Taming the code chaos, 2. Built-in versus user-defined packages, 3. Creating your own packages, 4. The access protection matrix, and 5. Packages in action. Okay, let's dive right into section 1, taming the code chaos, because we all know the pain of unorganized code, right? It's that feeling where everything collides and finding a single class feels like searching for a needle in a digital haystack.
So I want you to really ask yourself this. How do you organize hundreds or maybe even thousands of Java classes without completely losing your mind? When a project scales up, a flat directory structure just is not gonna cut it. You need a robust system. And our ultimate tool of sanity in Java is exactly what we're breaking down today.
That tool, of course, is the package. Think of a package kind of like a physical city's zoning laws, or maybe a highly organized corporate filing system. Instead of throwing every single document into one messy drawer, you organize a combination of classes, interfaces, and even sub-packages into distinct directories. You group them based on what they do, their functionality, their usability, and their category. It brings absolute order to the chaos. And why do we go through the trouble of organizing things this way? Well, there are 3 massive advantages. First up is reusability. If you write a brilliant piece of code, you can package it up and just simply import it anywhere you need it again. Write once, use everywhere. Second, better organization. In a massive project, you group similar classes so you can locate them instantly, which drastically improves your efficiency. And third, actually, this is a total lifesaver, resolving name conflicts. Imagine you have 2 classes, both named timer. In a flat folder, they just overwrite each other. But with packages, you can have a timer in an animation package and another timer in a database package, and they will never, ever collide.
Moving on to section 2, built-in versus user-defined. Let's take a look at the 2 major landscapes of packages out there. The ones Java provides for you right out of the box, and the ones you build all by yourself. So, the Java API's built-in packages are a huge part of what makes the language so incredibly powerful. Notice java.lang right at the top there. This contains the absolute fundamental language support, things like primitive types and math operations. In fact, it's so vital that Java actually automatically imports this into every single file you write, no coding required. Below that, you've got incredible tools ready to go. Java.io for reading and writing data, Java.util for essential data structures, your linked lists, dates, things like that. Then there's Java.awt for graphical interfaces, and Java.nets for networking. It's literally a goldmine of pre-written code. So we're looking at this pretty stark contrast. On one hand, built-in packages are those ready-made tools already defined as part of the Java API. On the other hand, we have user-defined packages. These are the custom logic environments, the specific namespaces that you, the developer, create entirely from scratch for your project's unique needs. Which brings us to section 3, creating your own packages. Now that we know what they are, let's get into the how-to. Let's walk through the procedure for setting up your very own user-defined namespaces. Defining a package is delightfully simple. We're talking just one line of code, the word package followed by your package name, ending with a semicolon. But, and this is a golden rule here, this command must be the absolute first statement in your Java source file. By doing this, you are explicitly telling the compiler that every single class declared within this file belongs to this specific namespace. Now, what's really fascinating here is how elegantly Java connects the virtual world of your code to the physical world of your computer's hard drive. You can create hierarchies using a dot, like java.awt.image. But here's the catch. That package hierarchy in your code must directly, perfectly translate to the file system directories on your OS. If you declare package java.awt.image, that Java file absolutely needs to be stored in a folder called image, which is inside a folder called awt, which is inside a folder called Java. The code structure and the folder structure have to mirror each other exactly. Okay, let's switch gears a bit.
Section 4, the Access Protection Matrix. We are transitioning from the folders, our packages, to the security bouncers that guard the data inside them.
Because packages and classes interact in some pretty complex ways, Java sets up 4 highly specific visibility zones, or categories, for accessing your data. You basically have to ask yourself, is the file trying to access my data a subclass in the same package? Is it just a standard class in the same package? Is it a subclass sitting in a totally different package? Or is it a class that is neither a subclass nor in the same package at all? These 4 scenarios determine exactly who gets in and who gets blocked.
I like to think of these access modifiers as a matrix of different types of security guards. Private is like a locked diary. If you aren't inside the exact same class, you get a hard, undeniable no. Public, on the other hand, is a billboard. Anyone, anywhere can see it. If you use no modifier at all, what we usually call default, it's kind of like a neighborhood watch. Anyone in the same package can access it, but outsiders cannot. And then there's protected. Protected acts like a VIP club. It lets your package neighbors in, for sure, but it also gives special access to subclasses that live completely out of town in totally different packages. So the absolutely crucial point here is understanding the difference between the extremes and those highly specific exceptions. Honestly, this is where I see the most confusion. Private is your strictest bouncer. It strictly forbids access outside its own class file. Protected, however, is your highly specific VIP bouncer. It generally protects your code from the outside world, but deliberately leaves a backdoor open for subclasses residing in entirely different packages. And this brilliantly illustrates what we're going to dive into next. Section 5, Packages in Action. Let's distill a 5-file code example to really see these bouncers doing their jobs. Imagine we have a base class over in package P1 with 4 integers, a private, a default, a protected, and a public. We also have 2 other files living in that exact same package. Derived.java is a subclass, and samepackage.java is just a standard, unrelated class. Because they are both in the exact same package as the base class, they both behave identically. They can comfortably access the default, the protected, and the public integers. But that private integer? No way. It's strictly off limits to both of them. But what happens when we cross package boundaries? Let's say we move over to package P2 and we're trying to look back at the data in package P1. Suddenly, everything changes. For other package.java, which is completely unrelated, the bouncer locks it out of almost everything. It can only see the public integer. But take a look at protection2.java. Because it uses the extends keyword to become a subclass, it gets that VIP treatment. Even though it's living in a totally different package, it actually retains access to the protected integer, right alongside the public one.
So how do we actually bring all these files to life? The sequential compilation flow is the secret sauce here. You write your code, and then you compile it. But pay close attention to that compilation command. javac-d dot filename.java. That -d dot part, -d dot, is basically a magic spell. When you run that, the Java compiler automatically creates the physical package directories, like those P1 and P2 folders, directly on your hard drive, and then automatically places the compiled class files right inside them. It does all the heavy lifting for you. Finally, once everything is compiled and securely sitting in its properly generated folders, you use an executive runner class, something like a pack demo file, to start the application. But because your files are now hidden away in their safe little namespaces, you have to explicitly invite them to the party. You do this using the import statement, explicitly bringing in exactly what you need from package P1 and package P2 to run the whole application smoothly. Take a second to think about what you've just mastered. You now have the exact blueprint to take thousands of scattered Java files, neatly organize them into logical directories, completely eliminate naming collisions, and strictly secure their data using access modifiers. The code chaos, it's completely gone. So I'll leave you with this provocative thought. If your code is now perfectly organized and tightly secured, what massive, complex system are you ready to build next? Thank you so much for joining me for this explainer, and happy coding.